The James Webb Space Telescope has just seen something it shouldn't have. When it looked deeper into the universe than ever before, it captured a signal that defied everything we thought we knew about the early cosmos, a light that shouldn't even exist so soon after the Big Bang. Astronomers were left stunned, questioning how such brightness could pierce through a universe that was supposed to be cloaked in darkness. Webb didn't just peer far back in time. It may have looked too deep, uncovering a secret that challenges the very foundations of cosmic history. And if you want to know the full story, then watch this video till the end and subscribe to the channel. Let's begin. Not long after this shocking realization, astronomers traced the mysterious signal to a single, astonishing source, a tiny ancient galaxy named Jade's GSZ 13-1. What makes this galaxy so extraordinary is its age. It existed just 330 million years after the Big Bang, when the universe was less than 3% of its current age. To put that in perspective, if the universe's history were compressed into a single year, Jade's GSZ 13-1 would have formed in the very first day of January. This wasn't supposed to happen so early. Galaxies simply weren't expected to organize themselves this quickly after creation. Yet, there it was, small, compact, and burning brightly across unimaginable distances. The James Webb Space Telescope detected this cosmic relic using its unmatched infrared vision. The light from Jade's GSZ 13-1 has been stretched by the expansion of the universe itself, shifting into longer wavelengths, a phenomenon known as redshift. And Webb measured that redshift to be around 13, meaning it's one of the earliest and most distant galaxies ever seen. Every photon Webb captured from it had traveled more than 13 billion years to reach us, carrying a message from a time when the first stars were just beginning to ignite. This wasn't just another galaxy. It was a window into an era that no other telescope had ever breached. What Webb saw in that faint glow wasn't merely ancient light. It was the universe whispering secrets from its own beginning. To truly grasp the magnitude of what Webb uncovered, we have to journey back to the time Jade's GSZ 13-1 existed, a period known as the Cosmic Dark Ages. After the Big Bang, the universe was a chaotic soup of energy and particles, expanding and cooling rapidly. For hundreds of millions of years, it remained an opaque, lightless void. There were no stars, no galaxies, just vast clouds of neutral hydrogen gas stretching endlessly across space. This hydrogen acted like a cosmic fog, trapping light and preventing it from traveling freely. Even if the first stars had tried to shine, their light would have been swallowed almost immediately by this dense veil. The Cosmic Dark Ages were, in essence, a time before transparency, a time when the universe was silent and sightless. Photons, the particles of light, couldn't move far without being absorbed or scattered. Space was not yet illuminated. It was a cold, dim expanse waiting for the first sparks of creation. Only when gravity began pulling matter together, igniting the very first stars, did the universe start to glow faintly through its own haze. But according to our previous understanding, that glow should have come much later, hundreds of millions of years after the era in which Jade's GSZ 13-1 was found shining. Which leads us to the most perplexing twist of all. Webb saw something it simply shouldn't have. Astronomers had long believed that during those first few 100 million years, light itself was essentially trapped, locked behind an impenetrable wall of hydrogen fog. The early universe, still thick with neutral atoms, was supposed to be completely opaque. Any photons produced by the first stars or nascent galaxies would have been absorbed almost instantly by that dense gas, never escaping to travel across space. For decades, This understanding formed one of the bedrock principles of cosmology, that before a certain threshold, before the epoch of reionization truly took hold, the cosmos was dark, silent, and blind. No light could cross the expanse. No signal could reach us. It was as if the universe had drawn a curtain across its earliest scenes, leaving astronomers forever guessing at what truly happened in that primordial darkness. So when the James Webb Space Telescope turned its gaze toward that ancient time, scientists expected to find only the faintest glimmers, traces of heat perhaps, or indirect signs of early star formation. They certainly did not expect to see clear, structured galaxies shining brightly through the haze. And yet, that's exactly what Webb found. The data came in slowly at first, pixel by pixel, light that had traveled across 13.4 billion years of cosmic expansion before finally striking Webb's gold-coated mirrors. At first, astronomers thought there must have been a mistake. The redshift readings were too high, the light too clear. According to established models, no light from such an early epoch should have reached us at all. The hydrogen fog should have devoured it long before it could cross even a fraction of that distance. But Webb's spectrometers told a different story. There was a sharp, undeniable signal, a very specific kind of light emission that, if confirmed, would defy decades of theoretical predictions. This wasn't random noise or background radiation. It wasn't the faint afterglow of the Big Bang, which cosmologists know as the cosmic microwave background. No, this was something far more specific and deliberate. A Lyman alpha emission line, the spectral fingerprint of hot, young stars ionizing the hydrogen around them. But that shouldn't have been possible in the first 300 million years. The universe at that time was supposed to be too dense, too full of neutral gas, too early in its evolution to allow such emissions to escape. The data essentially said there were already bright, active galaxies shining through the cosmic fog far earlier than anyone imagined. The research teams behind the discovery were stunned. Many astronomers had to check and recheck their instruments, suspecting calibration errors or contamination in the data. After all, if this detection was real, it didn't just mean there was a galaxy forming early. It meant light was escaping the fog far earlier than our theories predicted. The so-called curtain of hydrogen wasn't as thick or as uniform as we thought. Somewhere, somehow, pockets of the universe had already begun to clear. Think about that for a moment. In a time when the universe was still in its infancy, when matter was only beginning to coalesce, and stars were just flickering into existence, there were already regions transparent enough for light to travel billions of light years unimpeded. This was never supposed to happen. It was as if Webb had peered into a locked room, only to find a window already open. The implications were enormous. If this early light could reach us, then perhaps the universe's first stars formed sooner than we ever believed. Perhaps they were far more massive, hotter, and more efficient at ionizing the hydrogen around them. Or perhaps something else, something entirely new, was at play. Whatever the reason, the observation shattered the neat timeline cosmologists had drawn for the evolution of the early cosmos. In essence, Webb had looked too deep, and what it saw didn't just expand our knowledge, it broke our assumptions. The light from Jade's GSZ's 13.1 wasn't faint or struggling. It was vibrant, structured, and full of spectral detail. This meant the galaxy wasn't merely a small collection of primitive stars. It was an organized system, already forming complex structures just a few 100 million years after the Big Bang. That's like finding a fully grown tree sprouting in the ashes just moments after a forest fire. Astronomers began to realize that the universe's early epochs might not have been as dark or chaotic as they once thought. If galaxies like Jade's GSZ 13.1 were able to shine through the fog, then the so-called cosmic dark ages may have ended far sooner than expected. But how could that be? What mechanism could have cleared the hydrogen gas so quickly, allowing ultraviolet light to travel freely through space? This was the twist, the moment of revelation that transformed excitement into deep scientific unease. The early universe, according to Webb, wasn't behaving according to the rulebook. It wasn't following the gentle, gradual evolution we had modeled for decades. Instead, it seemed to have undergone a rapid transformation, one that made it transparent and luminous far earlier than any existing theory could explain. Suddenly, all eyes turned toward the strange, elusive Lyman alpha signal buried in the data. If this emission was real, if it truly came from JADE's GSZ 13.1, then our understanding of the universe's first billion years would need to be rewritten from scratch. The cosmos had begun revealing its secrets, but in doing so, it had posed one of the biggest mysteries in modern astrophysics. Webb had reached too far into time, too deep into the unknown, and what it found wasn't silence or darkness, but a defiant glow, a cosmic whisper from a universe far more mature than it should have been. And that was just the beginning of the mystery. To understand why Webb's discovery shook the foundations of modern cosmology, we need to delve into the nature of what it actually detected: the mysterious Lyman alpha emission. This isn't just any random glow or background radiation. It's one of the most important signatures in the entire universe for identifying the presence of young, energetic stars. The Lyman alpha line is like a cosmic fingerprint, a distinct wavelength of ultraviolet light, precisely 121.6 nanometers, emitted when a hydrogen atom's electron falls from its second energy level back down to the ground state. Every time this happens, a single photon of ultraviolet light bursts forth, a tiny flash of cosmic energy that carries the unmistakable mark of star formation. In the early universe, when the first stars ignited, they were unlike most stars we see today. These were population 3 stars, enormous, scorching, and short-lived behemoths that burned their hydrogen fuel with intense ferocity. Their radiation was so powerful that it could ionize the hydrogen around them, stripping electrons away from protons and creating regions of charged gas known as ionized bubbles. Within and around these bubbles, light like the Lyman alpha emission could finally escape, because the hydrogen was no longer neutral and opaque. In simpler terms, this emission acts like a beacon of cleared space, a sign that the surrounding fog has been thinned out or completely dissolved by the radiation of nearby stars. That's what made Webb's detection so astonishing. To observe Lyman alpha light coming from a galaxy as early as JADE's GSZ 13, one means that somehow this small patch of the cosmos had already become transparent. The hydrogen that should have been thick and light-blocking was instead ionized and clear, a state that shouldn't have existed yet according to our best models of cosmic evolution. The universe was supposed to still be shrouded in its hydrogen fog at that time, and the first stars should have been struggling to punch through it. But Webb's spectrographs didn't lie. They picked up the clean, distinct signal of Lyman alpha photons, meaning that somewhere, something had already begun to carve out visibility in the cosmic darkness. Imagine it this way: if the early universe was a vast, fog-covered landscape, the Lyman alpha emission is like the faint beam of a lighthouse cutting through the mist. It tells us not just that something is shining, but that the fog around it has already started to clear. Every photon Webb captured from that signal was evidence that the early universe was not uniform. It wasn't just one endless sea of hydrogen blocking light. Instead, it had pockets of clarity, zones where stars and galaxies had already ionized the surrounding gas. This discovery is far more than a technical detail. In cosmology, the presence or absence of Lyman alpha emission is a kind of cosmic thermometer. It tells us when and where the fog began to lift. Before Webb, the general consensus was that this clearing, called cosmic reionization, began perhaps around 500 to 600 million years after the Big Bang and continued gradually until about 1 billion years later. But now, with Jade's GSZ 13, one shining from just 330 million years post-Big Bang, that timeline has been thrown into chaos. If Lyman alpha light was escaping at such an early time, then one of two things must be true. Either the first galaxies formed and evolved far faster than we ever thought possible, generating enough ultraviolet radiation to clear their surroundings in record time, or our entire understanding of how hydrogen interacts with radiation in the young universe needs a serious rewrite. Both possibilities are extraordinary. Both force us to question assumptions that have guided astrophysics for decades. It's worth emphasizing just how delicate this detection is. Lyman alpha photons are notoriously easy to absorb. Even a thin wisp of neutral hydrogen can scatter or destroy them before they ever reach us. For Webb to detect such a strong signal from such an early epoch means that the environment around Jade's GSZ 13.1 wasn't just slightly transparent, it was remarkably clear. Something had cleaned the cosmic fog in that region with surprising efficiency. And that raises more questions than it answers. Could the galaxy itself have been powerful enough to ionize its surroundings so rapidly? Was it forming stars at an incredible rate, far higher than galaxies of its age were supposed to? Or could there have been another hidden source of energy, perhaps an early black hole emitting intense radiation that accelerated the process? No one knows for sure yet, but every new observation from Webb seems to add fuel to this growing puzzle. In essence, the Lyman alpha emission serves as both a messenger and a mystery. It tells us that the fog was already lifting in places where it shouldn't have been, hinting at forces or events we still don't fully comprehend. It's like finding a torch burning brightly in a cave that was thought to be sealed in total darkness. The light shouldn't be there. And yet, there it is, defying expectations and daring us to explain it. What Webb uncovered through this emission line isn't just a technical anomaly, it's a message from the dawn of time. It tells us that the early universe was more dynamic, more turbulent, and more alive than we ever dared to imagine. The cosmos was already pushing back against its own darkness, already making itself visible, long before we thought that was possible. And that realization leads directly to the most astonishing part of all. Because if the universe was already transparent enough for Lyman alpha light to escape, then the very fabric of our cosmic timeline might be wrong. The fog that was supposed to hide the first galaxies may have lifted long before we thought it could. What makes this discovery so utterly shocking isn't just what Webb saw, it's when it saw it. According to every cosmological model built over the last half-century, the universe at 330 million years after the Big Bang should have still been dense, opaque, and unforgiving to light. The hydrogen that filled space during that time acted like a cosmic fog machine, scattering and absorbing ultraviolet radiation. Photons from the earliest stars shouldn't have had a chance. They should have bounced endlessly off atoms, trapped in a murky prison of hydrogen for hundreds of millions of years before the cosmos began to clear. And yet, Webb's instruments recorded a crisp, unmistakable Lyman alpha emission, the very light that shouldn't have been able to escape. This was not a faint, ambiguous signal barely above the noise. It was distinct, structured, and strong enough to leave no doubt. Light from Jade's GSZ 13.1 had travelled across 13.4 billion years of expanding space and somehow avoided being swallowed by the fog of the early cosmos. The mere existence of that light at such a redshift was like finding a clear, bright lighthouse beam cutting through a storm that should have been too thick to see through. This is why scientists were left speechless. The transparency of the early universe was supposed to evolve slowly. At that point in cosmic history, the fog of neutral hydrogen should have been almost completely opaque to ultraviolet photons, the same photons that create the Lyman alpha emission. In fact, the very models that describe the evolution of the cosmos are built on this assumption. The timeline is supposed to go something like this. After the Big Bang, the universe expands and cools, neutral hydrogen forms, and darkness reigns. Hundreds of millions of years later, the first stars appear. Their light begins to ionize the hydrogen around them. And only then, after a long, gradual process, does the fog start to lift. But Webb's data blew that timeline apart. If Lyman alpha light was escaping from JADE's GSZ 13.1, that meant the hydrogen in that region had already been ionized, already made transparent, long before the universe was supposed to allow it. The cosmos, it seemed, had cleared its throat and begun speaking far earlier than we were prepared to hear. Imagine walking through a dense, early morning fog, so thick you can barely see your own hand. Now imagine spotting a distant campfire glowing clearly through that same fog, so sharply that you can even make out its flickering patterns. You'd immediately realize that something must have changed in the air between you and that flame. The fog had to have thinned, even if everything you knew told you it was still dense. That's what astronomers felt when they saw Webb's data. Awe, confusion, and a creeping realization that the rules governing our universe's early light might not be what we thought they were. The transparency problem revealed by this discovery cuts to the core of cosmology. It suggests that reionization, the process by which the universe transitioned from opaque to transparent, either began much earlier than models predict or happened much faster than expected. For decades, scientists thought this process took hundreds of millions of years, beginning around redshift 10 or 9 and finishing near redshift 6. But JADE's GSZ 13.1, with its confirmed redshift of 13, was shining freely even earlier than that. It's as if we've stumbled across the universe's reionization fast lane, where everything cleared out ahead of schedule. What's even more unsettling is that JADE's GSZ 13-1 isn't alone. Webb has begun detecting other ancient galaxies, showing hints of similar early clarity, suggesting this might not be a one-off anomaly. This could mean that early galaxy formation and ionization were far more complex and localized than we realized. Perhaps the universe didn't reionize all at once, like a light switch turning on, but rather in patches, like islands of light forming in a sea of darkness. Each patch could have been a small, isolated region of ionized space, with its own early stars blazing through the fog. Still, one fact remains undeniable. By the time the light from JADE's GSZ 13.1 began its journey to us, the fog in that area of the cosmos was already lifting. That means the mechanisms of cosmic evolution were operating at a pace no one predicted. Either the first stars were far more massive and energetic than expected, or some other force was helping to thin the hydrogen veil faster than our models allow. Some theories even suggest that early black holes, tiny but ferocious, could have played a role, their radiation punching holes in the hydrogen gas around them and accelerating the transparency of the universe. The shockwaves from this discovery spread quickly through the astrophysical community. Scientists who'd spent their careers modeling the timing of reionization suddenly found themselves re-evaluating everything. How could light travel through a universe that was supposed to be opaque? Were our assumptions about the density of early hydrogen wrong? Or had we fundamentally misunderstood the nature of those first galaxies? In truth, the Lyman alpha signal from JADE's GSZ 13.1 doesn't just represent a galaxy seen across time. It represents a contradiction, a cosmic paradox, glowing billions of light years away. It tells us that the early universe may have been more porous, more dynamic, and more chaotically beautiful than we ever imagined. It also reminds us that the universe doesn't conform to our expectations. It behaves according to its own laws, revealing its secrets only when we have instruments powerful enough and imaginations open enough to see beyond the boundaries of theory. That's why this discovery is so profound. The Lyman alpha light shouldn't exist at that distance, not according to the textbooks. Yet, there it is, shining defiantly from the cosmic dawn, a whisper from a time when there should have been silence. Webb didn't just capture ancient light. It exposed a flaw in our understanding of how the universe transitioned from darkness to brilliance. The telescope didn't just see the unseeable, it saw the impossible. And that impossible light has become one of the greatest scientific puzzles of our time, forcing us to rethink not only how early galaxies formed, but when the universe first allowed itself to be seen. To make sense of what Webb's data revealed, let's picture the early universe not as a vast emptiness, but as a dense, endless ocean of cosmic fog. This fog wasn't made of water vapor. It was made of neutral hydrogen, the simplest and most abundant element in the cosmos, and yet the most effective at smothering light. Every time a newborn star tried to shine its first rays into the darkness, this fog absorbed them, scattering their photons in all directions. For hundreds of millions of years, it was as if the universe itself were wrapped in a thick veil, hiding its own beginnings from view. This was the cosmic dark ages, a time when the universe existed, expanded, and evolved, but could not yet be seen. Light was trapped in a cage of hydrogen. The photons that would one day tell us the story of the first stars and galaxies couldn't escape their prison. They were forever bouncing between atoms, unable to travel across space. In this fog-filled universe, visibility was almost non-existent. The first sources of light were more like whispers than shouts, drowned in the dense murmur of neutral gas. That's why the discovery of Lyman alpha light from JADES GSE 13.1 hit the scientific world like a thunderclap. It was clear, direct evidence that somewhere within that fog, a break had formed. The veil that was supposed to hide the cosmos's earliest creations wasn't completely uniform. It had holes, cracks, and clearings. Something had already started to burn the fog away. If the early universe was a cold, fog-covered landscape, then what Webb saw was a beam of sunlight breaking through before dawn. That light wasn't supposed to exist yet. The first stars were thought to have been too young and too few to clear the fog on such a large scale. It should have taken hundreds of millions of years for enough ultraviolet radiation to accumulate and ionize the hydrogen gas, turning it transparent. But Webb's observations showed that this process, this clearing of the cosmic mist, was happening far earlier than theory allowed. Neutral hydrogen behaves like a cosmic curtain. It blocks ultraviolet light, especially the Lyman alpha wavelength, almost perfectly. That means, in the simplest terms, if you detect Lyman alpha light from a galaxy, you know that the hydrogen between you and that galaxy has already become ionized, no longer neutral, no longer fog-like. So when Webb picked up that emission from JADES GSE 13.1, it meant one thing unmistakably. In that small corner of the early universe, the fog was already lifting. This is a revolutionary realization, because it tells us the universe was not a smooth, uniform expanse of identical conditions. Instead, it was patchy, a mosaic of dark and light regions, with some zones still steeped in hydrogen fog, while others had already begun to clear. The galaxy, JADES GSE 13-1, may have been sitting in one of those early clear bubbles, a pocket of ionized space carved out by powerful radiation from its own stars. In other words, it wasn't just shining, it was changing the environment around it. Imagine a night shrouded in thick fog, so heavy you can barely see your feet. Then, somewhere in the distance, a single bright lamp turns on. Its light doesn't travel far at first, but slowly it starts to push back the haze, revealing outlines, shadows, and space where before there was only grey. That's what these first galaxies were doing, illuminating the universe itself. Their starlight was the chisel that began carving structure into the cosmic void. But this metaphorical fog wasn't supposed to thin so soon. According to older models, the process of cosmic reionization, when starlight first cleared the hydrogen, should have peaked hundreds of millions of years ago, years later, long after the time of Jade's GSZ 13-1. The universe back then should still have been almost entirely opaque. Webb's detection shattered that assumption. It proved that some regions of the universe were already transparent only 330 million years after the Big Bang, at least 200 million years earlier than the leading theories predicted. This single observation means our models of the early universe are missing something fundamental. Either galaxies formed faster, producing immense radiation that cleared the fog early, or the fog itself was not as dense and uniform as previously thought. Perhaps turbulence in the early cosmos, driven by dark matter or the first black holes, created channels, thin corridors through which light could escape sooner than expected. Whatever the cause, the result is the same. The universe became visible earlier than it was supposed to. The fog analogy also helps us grasp the emotional weight of this revelation. For generations, scientists have tried to see through that primordial mist using radio telescopes, microwave background maps, and computer simulations. They were like sailors trying to navigate a starless sea, guided only by faint echoes of ancient light. Then, suddenly, the James Webb Space Telescope arrives, and with one observation, the fog parts. We can finally glimpse the first cosmic shorelines, the flickering lights of the first galaxies emerging from darkness. This isn't just a scientific achievement, it's a poetic one. Humanity, after billions of years, has finally begun to see the moment when the universe's first light fought its way through the fog of creation. It's a moment that bridges science and wonder, a reminder that the cosmos, even in its infancy, was already striving toward illumination. And yet, for all its beauty, this discovery also carries profound mystery. If the fog was clearing so early, what caused it? What were these first galaxies really like? So powerful that they could ionize vast regions of space in just a few 100 million years. Could there have been other sources of light, early quasars, black holes, or exotic phenomena, that helped accelerate the clearing? The fog may be lifting, but the questions it leaves behind are thicker than ever. Because if the universe was already this transparent, this structured, this awake, then our entire timeline of cosmic evolution must be re-examined. The light from Jade's GSZ 13-1 isn't just illuminating the early universe, it's illuminating the limits of our understanding. The James Webb Space Telescope didn't just find a galaxy, it found a window through the fog, and what lies beyond that window is forcing us to rewrite the story of how the universe learned to shine. To understand the magnitude of what the James Webb Space Telescope has uncovered, we need to explore one of the most important transitions in the history of the universe, a process known as cosmic reionization. This was not just another step in cosmic evolution. It was the moment the universe became visible, the dawn when light began to travel freely across space for the first time since the Big Bang. In the beginning, after the universe expanded and cooled enough for protons and electrons to combine into neutral hydrogen atoms, everything went dark. This was the start of the cosmic dark ages, a time when the universe was filled with neutral hydrogen gas that absorbed and scattered all high-energy radiation. The cosmos existed, but it was hidden behind its own fog. Stars had not yet been born, galaxies had not yet formed, and photons, those tiny messengers of light, couldn't move more than a few feet without being captured by a hydrogen atom. For hundreds of millions of years, the universe was a lightless ocean of invisible matter. Then, something extraordinary happened. Gravity, the silent architect of the cosmos, began pulling matter together into clumps. These clumps became the first stars, gigantic, short-lived beacons burning with unimaginable heat. Their light was so powerful that it didn't just illuminate their surroundings. It began to transform the universe itself. The intense ultraviolet radiation from these stars and the first galaxies started ripping electrons away from hydrogen atoms, ionizing them. This process turned the foggy, opaque hydrogen gas into a transparent plasma through which light could finally pass. This grand transformation is what scientists call reionization. It's the era when the universe transitioned from darkness to light, when the first cosmic fog lifted, allowing photons to travel unimpeded through space. It was the universe's coming of age, the moment when cosmic structure, starlight, and visibility all began to bloom together. Now, for decades, cosmologists believed they had pinned down the approximate timing of this event. Based on older observations from the Hubble Space Telescope, the Planck satellite, and ground-based surveys, reionization was thought to begin roughly 400 to 500 million years after the Big Bang, reaching completion around 1 billion years later. In that traditional picture, galaxies like Jade's GSZ 13.1 simply shouldn't have existed early enough to make any difference. The fog should still have been thick, the hydrogen neutral, and the light trapped. But Webb's discovery changes that story dramatically. The detection of Lyman alpha emission from Jade's GSZ 13-1, a galaxy existing only 330 million years after the Big Bang, tells us that reionization had already begun. That means the universe was clearing far earlier than we thought possible. The radiation from this tiny ancient galaxy was strong enough to ionize its local environment, punching a hole in the fog of hydrogen and creating a small, transparent window through which its light escaped. This isn't a minor adjustment to our cosmic timeline. It's a paradigm shift. It implies that the process of reionization might have started almost 100 million years earlier than models had predicted. That's an enormous difference when dealing with the earliest epochs of the universe. It's as though the universe woke up before schedule, lighting up far sooner than anyone anticipated. To put it in perspective, if the entire history of the universe were compressed into a single 24-hour day, the Big Bang would happen at midnight, Earth would form around 3:30 in the afternoon, and humans would appear in the last few seconds before midnight the next day. In that timeline, reionization, the moment the universe became transparent, was supposed to happen around 12:05 a.m., just after the first minute of the cosmic clock. But Webb's discovery suggests that light started piercing the darkness closer to 12:30 a.m., an astonishingly early awakening. So why is this so shocking? Because everything about our models, the density of hydrogen, the expected rate of star formation, even the basic physics of early structure formation, depended on reionization happening later. If it began earlier, then something about our understanding of the early universe is incomplete. Maybe the first stars were far more massive and luminous than we imagined, producing torrents of ionizing radiation. Maybe the first galaxies were forming in greater numbers or clustering together more effectively, accelerating the clearing process. Or perhaps entirely new mechanisms, such as early quasars or black holes, were contributing to the early reionization of space. Whatever the cause, one thing is clear. The universe wasn't the static, predictable environment we once thought it was. It was dynamic, violent, and fast evolving, changing conditions in just a few 100 million years. The cosmic fog wasn't lifting evenly across space either. It likely cleared in patches, with bubbles of ionized gas expanding around early galaxies, like islands of light growing in a dark ocean. Jade's GSZ 13-1 may have existed inside one of these islands, an early bubble of clarity in an otherwise foggy cosmos. This revelation has massive implications for cosmology, because reionization defines the boundary between two entirely different eras of the universe. Before it, space was a murky, opaque void. After it, the universe became transparent and light could travel freely, eventually reaching us billions of years later. To detect signs of reionization already underway at such an early epoch is to glimpse the very moment when the cosmic lights turned on. It's hard to overstate the emotional weight of this discovery. For centuries, humans have looked at the night sky and wondered when and how the first stars were born. The James Webb Space Telescope has now given us the answer, and it's far earlier, far brighter, and far more dramatic than we dared to believe. The universe didn't wait patiently to become transparent. It raced toward illumination, bursting into light long before we were ready to see it. In a single observation, Webb has redefined one of the most important turning points in cosmic history. Reionization didn't just happen. It happened early, fast, and fiercely. And as we look deeper into Webb's data, one truth becomes unavoidable. The universe has been keeping secrets about its own awakening, and we've only just begun to uncover them. If the discovery of early reionization shocked astronomers, what came next shook the very foundation of cosmology itself. Because if Jade's GSZ 13-1 was already shining through the fog at just 330 million years after the Big Bang, that could only mean one thing: our models of the early universe, and especially our understanding of cosmic reionization, are incomplete or perhaps even wrong. For decades, cosmologists have built detailed simulations of how the first light emerged, when the first stars formed, and how those stars transformed the universe. These models relied on equations that carefully balanced the rate of star formation, the density of neutral hydrogen, the strength of ultraviolet radiation, and the gravitational growth of cosmic structure. Everything fit together neatly, at least until the James Webb Space Telescope looked deeper than ever before and found something that shouldn't exist yet. Now, astronomers are forced to confront an unsettling question. Was the early universe lighting up faster than we thought? According to the most widely accepted picture, the first galaxies were supposed to grow slowly. The earliest stars, massive, short-lived, and metal-free, would begin to ionize their surroundings, but the effect should have been small and localized. Only after hundreds of millions of years of steady star formation would enough ultraviolet radiation build up to push back the cosmic fog on a large scale. But Webb's observations suggest that by the time the universe was just a few 100 million years old, at least some regions were already bright, clear, and teeming with galaxies capable of blasting through the neutral hydrogen that filled space. That doesn't just speed up the cosmic timeline, it upends it. The models developed from Hubble and Planck data told us that the universe's transition from opaque to transparent, the epoch of reionization, should have occurred between about 400 million and 1 billion years after the Big Bang. During that time, light from early galaxies would gradually carve ionized bubbles in the fog, expanding and merging until the universe became transparent everywhere. But Webb's detection of Lyman alpha emission from Jade's GSZ 13-1 shows that those clear patches already existed earlier than our best estimates by at least 100 million years. That's a huge discrepancy, one that implies our understanding of how fast galaxies form, how bright they are, and how efficiently they ionize their surroundings is deeply flawed. Perhaps our assumptions about the density and uniformity of hydrogen in the early cosmos were wrong. Maybe the fog wasn't as thick as we thought, or maybe it wasn't evenly distributed. The universe could have been patchy from the very beginning, with certain regions evolving faster due to local variations in density, gravity, or radiation. In those hot spots, galaxies might have formed more quickly, creating pockets of transparency that appeared far ahead of schedule. Alternatively, maybe the stars in those early galaxies were nothing like the ones we see today. Some theorists now believe that the first stars, the so-called population 3 stars, could have been hundreds of times more massive than our Sun, blazing at temperatures that made them incredibly efficient at ionizing hydrogen. These titanic stars would have lived fast and died young, exploding as supernovae that enriched their surroundings with heavier elements, paving the way for second-generation stars and early galaxy formation. If that's true, then Webb's observations might be our first real glimpse of this lost generation of cosmic giants. But there's another, even more radical possibility. Maybe something entirely new is happening. Perhaps black holes or primordial quasars were contributing far more radiation than our models accounted for. A single actively feeding black hole, even a small one, could pour out enormous amounts of ionizing energy, clearing hydrogen much faster than ordinary starlight could. If early galaxies contained many such black holes, the universe might have brightened and cleared much earlier than anyone expected. Whatever the cause, the conclusion is unavoidable. Our existing frameworks for cosmic evolution can't fully explain what Webb has seen. The equations still balance on paper, but the cosmos itself is telling a different story, one of rapid transformation, accelerated light, and early structure that defies traditional chronology. It's as if the universe didn't ease into illumination, but raced toward it. This forces astronomers to reconsider every assumption about how fast matter condensed into stars, how efficiently those stars produced ionizing light, and how quickly that light could escape into the surrounding space. It also challenges the very nature of the cosmic dawn, that pivotal era when the first galaxies began to shape the modern universe. Instead of a slow sunrise, we may have witnessed something closer to a sudden burst of brightness, a cascade of formation and illumination that swept across space like a wave of fire through fog. But perhaps the most haunting aspect of all this is what it implies about our own scientific limitations. For so long, we've treated the universe as predictable, governed by equations we could write down, timelines we could chart, and phenomena we could forecast. Yet Webb's deep field vision has shown us that the universe is not a clockwork machine ticking neatly through history. It's an unfolding mystery, full of surprises, contradictions, and revelations that remind us how little we truly know. If galaxies like Jade's GSIZ 13.1 were already bright enough to ionize their surroundings so early, then the rate of cosmic evolution was not gradual, but explosive. The universe was alive and active far earlier than we ever imagined. A turbulent, brilliant frontier filled with light that shouldn't have been able to shine. So yes, perhaps the early universe was lighting up faster than we thought. But that question opens a deeper one, not just about the speed of light's emergence, but about the very structure of reality in its infancy. Were we wrong about how matter gathered? About how radiation traveled? About how darkness gave way to illumination? Webb's discovery doesn't just challenge our models of reionization, it challenges our sense of certainty itself. Every time we think we've reached the edge of understanding, the universe moves that edge farther away. And as Webb peers deeper still, we're beginning to see that the cosmos was never a place of quiet beginnings. It was a storm, a radiant, violent surge of creation that tore through darkness long before the rules we wrote could catch up. The galaxy that sparked all this cosmic upheaval, JADES-GS-Z 13-1, wasn't discovered by chance. It emerged from one of the most ambitious and technically sophisticated astronomical programs ever undertaken, the JWST Advanced Deep Extragalactic Survey, better known as JADES. JADES is, in essence, a deep archaeological dig into the fabric of the cosmos, a methodical, high-precision effort to uncover the universe's oldest and faintest structures. Led by a global collaboration of astronomers from the European Southern Observatory, NASA, and dozens of leading research institutions, the survey uses Webb's unparalleled infrared instruments to map ancient galaxies that existed within the first few 100 million years after the Big Bang. Its goal is nothing less than to reconstruct the timeline of cosmic dawn, the era when the first stars and galaxies transformed a dark, featureless universe into one filled with light, complexity, and structure. To do this, JADES focuses on two regions of the sky that have become legendary in observational astronomy: the Hubble Ultra Deep Field and the Good South Field, the Great Observatory's Origins Deep Survey. These are tiny, seemingly empty patches of sky that, when viewed with powerful telescopes, explode with thousands of distant galaxies, each one a frozen echo of the past. The James Webb Space Telescope takes this concept to an entirely new level. Where Hubble could peer back about 13 billion years, Webb can see even farther, not just to galaxies near the beginning of time, but into the time when the universe was just beginning to form them. The JADES survey is the scientific equivalent of opening a time capsule buried at the dawn of existence. It uses Webb's near-infrared camera, NIRCAM, and near-infrared spectrograph, NIRSPEC, to observe faint light stretched across unimaginable distances by the expansion of space. That stretching, the cosmological redshift, shifts visible and ultraviolet light into the infrared spectrum, allowing Webb to detect it. By capturing this light, JADES provides astronomers with both images and spectra, enabling them to measure redshifts precisely, determine the chemical compositions of galaxies, and estimate their ages, masses, and rates of star formation. JADES GS-ZIS 13.1, the now famous galaxy that turned theory on its head, was first identified in the survey's ultra-deep field observations as a small, faint smudge of light. At first glance, it looked like just another candidate galaxy among thousands. But when Webb's spectrograph analyzed its light, it became clear that this faint smudge was extraordinary. The data revealed a redshift of Z equals 13.2, meaning the light we see from it began its journey only 330 million years after the Big Bang. That makes it not only one of the earliest galaxies ever observed, but also one of the most well-defined examples of early structure formation in the known universe. The purpose of JADES, however, extends beyond the discovery of individual galaxies. Its mission is to map the evolution of galaxies through time, connecting the earliest structures to those we see in the modern cosmos. By studying hundreds of ancient galaxies like JADES GSZ 13.1, astronomers can piece together how gas turned into stars, how stars grouped into galaxies, and how those galaxies interacted, merged, and evolved. In doing so, JADES is essentially building the cosmic family tree, tracing the ancestry of the Milky Way and every galaxy we see today back to their primordial origins. But JADES is doing something even more profound than that. It's providing observational anchors for the theoretical models that describe the universe's early development. Until Webb, our picture of the early universe was largely based on simulations, mathematical recreations of how matter and radiation might have behaved. Those simulations relied on assumptions about the number of early galaxies, their brightness, and their ability to emit light strong enough to ionize hydrogen. JADES is now providing hard data to test those assumptions, and so far the data doesn't fit the models neatly. Instead of a sparse, dim, early universe filled with slow-forming galaxies, JADES is revealing a crowded, dynamic cosmos, filled with bright, compact galaxies appearing much sooner than expected. It's as if the universe, in its infancy, was already bursting with creative energy, forming stars and structures in rapid succession. Each discovery forces scientists to adjust their models, to question how the universe organized itself so quickly, and what forces might have accelerated that growth. The implications extend far beyond any single galaxy. If the JADES survey continues to find galaxies at such extreme redshifts, and there are already candidates beyond Z equals 14, it could mean that the first generation of galaxies formed almost immediately after the Big Bang, perhaps within just 200 million years. That would compress the timeline of cosmic evolution dramatically, suggesting that the universe was capable of assembling complex structures almost as soon as the first atoms existed. To achieve such sensitivity, JADES pushes the limits of Webb's design. Each image in the survey represents tens of hours of exposure time, sometimes stacked over multiple sessions to gather enough light from these faint, ancient sources. The result is a dataset of staggering depth and precision, a 3D map of the universe stretching across more than 13 billion years of history. Every pixel in those images is a story, every faint glimmer a clue to how matter, light, and gravity collaborated to sculpt everything we see around us. JADES doesn't just study galaxies, it studies time itself. It is peeling back the layers of cosmic history, showing us the first flickers of light that pierce the universal night. And as Webb continues to feed new data into the survey, the surprises keep coming. More galaxies, more complexity, more contradictions to what we thought we knew. JADES GS 13.1 was the first to shout from the darkness, but it likely won't be the last. If Webb continues to reveal galaxies forming so early and shining so brightly, we'll have no choice but to rewrite the cosmic timeline, perhaps even the physics that underpin it. The JADES survey is not just a project of observation, it's a project of revelation, one that is redefining our understanding of the universe's very first moments of light. And that's what makes it so extraordinary. Every frame of data it collects brings us closer to answering humanity's oldest question: when did the universe first begin to shine? What truly sets the James Webb Space Telescope apart, what makes it more than just a successor to Hubble, is its extraordinary ability to see light that has been stretched by time itself. Webb was designed from the ground up to do something no other telescope in human history could: look back so far, so deep into the past, that it can witness the first moments when the universe began to shine. It can see galaxies not as they are today, but as they were billions of years ago, when they were newly born in the chaos following the Big Bang. To understand how this works, we have to remember that the universe is not static. Space itself is expanding, stretching continuously in all directions, carrying galaxies farther and farther apart. As that expansion happens, it doesn't just move objects through space, it stretches light. Every photon traveling through the cosmos is caught in this expansion, and as space expands, the light's wavelength grows longer, shifting it toward the red end of the spectrum. This phenomenon is known as cosmological redshift, and it's the key that allows Webb to peer across time. The further away a galaxy is, the longer its light has been traveling to reach us, and the more its wavelengths have been stretched by cosmic expansion. Light that began its journey as intense ultraviolet radiation from young stars billions of years ago has now been stretched into the infrared range by the time it arrives at Earth. That means that to see the earliest galaxies, the ones forming just a few 100 million years after the Big Bang, we can't use visible light telescopes like Hubble. We need an instrument that can capture infrared light, the kind that carries the ancient echoes of the universe's earliest epochs. This is where the James Webb Space Telescope becomes a time machine. Webb's 6.5-meter mirror, made of 18 hexagonal segments coated in gold for maximum infrared reflectivity, collects this faint, stretched light from across the cosmos. Its instruments, the Near-Infrared Camera, NIRCAM, the Near-Infrared Spectrograph, NIRSPEC, and the Mid-Infrared Instrument, MIRI, are all finely tuned to detect and analyze these wavelengths. Together, they allow Webb not only to see the earliest galaxies, but to decode their light, to measure their redshifts, determine their ages, and even analyze their chemical compositions. When Webb looks at a distant galaxy, it's not seeing it as it exists today. It's seeing it as it was billions of years ago, because that's how long the light has taken to reach us. For galaxies like Jade's GSAS 13.1, that means Webb is effectively looking back more than 13.4 billion years into history, just a few 100 million years after the Big Bang. In human terms, that's like looking back, not just to your childhood, but to the moment you were born and seeing it unfold in real time. What's even more astonishing is the sensitivity of Webb's detectors. It can capture photons that have traveled across nearly the entire history of the universe, photons that left their sources long before our solar system, our planet, or even our galaxy existed. These are the oldest messengers in existence, carrying information from a time when the cosmos was still forming its first structures. But Webb's infrared vision doesn't just let it see farther, it lets it see through. Infrared light can penetrate clouds of dust and gas that block visible light. In the early universe, galaxies were enshrouded in thick cocoons of gas, making them invisible to telescopes that observe in optical wavelengths. Hubble, for all its brilliance, was limited by this barrier. It could detect galaxies up to a certain redshift, but beyond that, the light was simply too stretched, too faint, too buried in dust. Webb overcomes that obstacle completely. Its infrared instruments can peer through those ancient veils, revealing galaxies that were once hidden from sight. This is why, within just months of its first deep-field images, Webb began rewriting cosmic history. It found galaxies that were not only older than we expected, but more developed. These galaxies already had structure, density, and brightness that seemed to belong to a universe far more mature than it should have been at that early stage. The infrared vision of Webb allowed humanity to see a universe that wasn't dark and empty, but already ablaze with light and activity mere moments after its birth. Every time Webb takes a deep-field image, what we're looking at isn't a snapshot of distant space. It's a timeline, a layered portrait of the universe through the ages. The galaxies nearest to us appear as they are now, but each step deeper into the image takes us further back in time. The faintest, most distant specks of light, some no larger than a pixel, are the earliest galaxies ever to exist. Each of those faint glimmers represents billions of suns, billions of years in the making, and photons that began their journey long before our own Milky Way formed. It's easy to forget, staring at those stunning Webb images, that what we're actually seeing are fossils of light, ancient radiation preserved across cosmic time. The telescope's infrared capabilities have effectively pierced the veil of eternity, allowing us to glimpse the universe's own childhood. And this isn't metaphor. Every observation Webb makes is a direct measurement of time and transformation, each photon a physical record of how space and matter evolved. And because of this, Webb isn't just expanding our understanding of astronomy, it's expanding the boundaries of human perception. It's allowing us to look back further than our eyes, our technology, or even our imagination could once reach. When we see galaxies like Jade's GSZ's 13.1, we are witnessing the moment the first lights turned on in the universe. We are looking at the dawn of everything. No other telescope has ever been able to do this. Hubble showed us the cosmos as it is. Webb is showing us the cosmos as it was becoming. Its infrared vision doesn't just reveal what's out there. It reveals who we are, where we came from, and how the universe transformed from darkness into light. That is what makes Webb so special. It is not merely a machine of observation. It is a bridge across time, connecting the present to the moment creation first began to glow. When the James Webb Space Telescope began its mission, scientists believed they had a fairly clear roadmap of what it would find. They expected to see faint, primitive galaxies, small clusters of newly formed stars struggling to emerge from the thick hydrogen fog that once blanketed the early cosmos. But as Webb stared deeper, collecting ancient photons that had travelled for nearly the entire age of the universe, something unexpected happened. It began to see too much. The telescope had, in a sense, locked too deep into the universe's past. It looked so far back in time that it began to uncover a reality that didn't quite match our predictions. A cosmic history that defied our models, our equations, and even our expectations of how the universe should behave. This phrase, "looked too deep," has become more than a poetic turn of phrase among astronomers. It has become a metaphor for what happens when human curiosity goes beyond the limits of what we think we understand. Webb's mirrors didn't just peer into the past, they peered through it, into layers of space-time where the laws we thought governed cosmic evolution seemed to unravel. At these unimaginable distances, the telescope's instruments are detecting galaxies that should be impossible, fully formed systems appearing when the universe should still have been assembling its first building blocks. Massive, bright, complex galaxies like Jade's GSZ 13.1 and others like it weren't supposed to exist so soon after the Big Bang. The models had been clear. Structure formation takes time. First come stars, then clusters, then small proto-galaxies that slowly merge into the grand spirals and ellipticals we see today. Yet Webb's deep field images showed something far more chaotic and advanced, as if the universe had fast-forwarded through its own early evolution. It's as if Webb has opened a forbidden door in time, one that reveals a version of the early universe no one was prepared for. It's seeing light that, by all accounts, shouldn't have been able to travel this far yet. It's revealing galaxies that are too bright, too organized, and too large for such a young cosmos. And with every new observation, that pattern continues. The deeper Webb looks, the more anomalies it finds. To the scientists studying this data, the experience is as thrilling as it is unsettling. Imagine spending decades crafting the most sophisticated cosmic timeline humanity has ever built, only to have a single instrument pierce through it and whisper, "You were wrong." Webb didn't just look deep, it locked its gaze into a time so ancient, so raw, that it began peeling back the very assumptions that have guided astronomy for generations. In this sense, locked too deep is both a scientific and philosophical turning point. For centuries, we've pushed our tools to see farther and farther into space, believing that distance equates to understanding, that if we could just look deep enough, we'd find the neat beginning of everything. But Webb's data suggests that the cosmos doesn't reveal its origins in simple linear layers. Instead, it's showing us a tangled web of light and structure, as if the early universe was far more mature, interconnected, and luminous than we've ever imagined. This revelation strikes at the heart of our cosmic narrative. If the first galaxies were already so bright and structured, then the story of the universe's infancy is more complex and more turbulent than we believed. Perhaps cosmic reionization wasn't a slow, graceful dawn, but an explosive awakening. Maybe the first stars were so massive that they burned through the darkness almost instantly, creating brilliant pockets of ionized space long before we expected them to. Or maybe the rules of physics themselves, as they applied in those early epochs, aren't quite what we think they are. In a way, Webb has become a mirror not just for the cosmos, but for us. When it looked too deep, it didn't just reveal new galaxies. It revealed the limits of our knowledge, the fragility of our assumptions, and the awe that comes with realizing how much more there is to learn. It's as though humanity has finally reached the edge of the map labeled, "Here be dragons." And instead of finding nothing, we found something impossibly beautiful and confusing staring back. Webb's view is so profound, so penetrating, that it's now confronting astronomers with data that challenges the very structure of cosmology, the framework that has defined how we understand time, matter, and light itself. This is not just another discovery, it's a confrontation with the unknown. The universe, once thought to be a clockwork machine, is proving to be a living, unpredictable entity, one that defies neat categorization. When Webb locked too deep into the fabric of reality, it became clear that the cosmos isn't what we expected it to be. It's more ancient, more luminous, and perhaps more alive than we dared to imagine. The telescope has become a kind of cosmic truth teller, revealing that our most cherished models are only fragments of a larger, grander picture, one that stretches beyond the boundaries of our imagination. In a poetic sense, Webb's locked too deep discovery is humanity's own moment of reflection. It's as if we've been staring at a mirror made of starlight and, for the first time, seen the universe looking back, not as a distant mystery, but as a dynamic story still unfolding, full of twists we never anticipated. And as that story continues to unfold, one truth grows clearer. The deeper we look, the more the cosmos surprises us. Webb has shown us that the universe is not a static past. It's a living memory, still echoing with the energy of its own creation. The light we see now is not just ancient, it's alive with the tension between what we thought we knew and what we're only beginning to discover. The telescope has, quite literally, locked too deep, and in doing so, it has begun to unlock the universe's most profound secrets. So if the James Webb Space Telescope really has looked too deep, if it's peering into a universe that seems to be breaking its own rules, then the next question naturally becomes, why? How is it possible that galaxies like Jade's GSC 13-1 were already shining so brightly, so early, in a universe that was supposed to be buried in hydrogen fog? What could possibly explain this cosmic contradiction? Astronomers have put forward several leading theories, each more fascinating and more unsettling than the last. Some are grounded in extensions of existing models. Others venture into territory that could reshape our understanding of physics itself. But all of them attempt to answer one fundamental question. How did the early universe become visible so quickly? The first and most straightforward possibility is that galaxies formed earlier than expected. For decades, cosmological models assumed that after the Big Bang, it would take hundreds of millions of years for gravity to pull enough matter together to form the first stable galaxies. Early stars, the so-called population 3 stars, were expected to be rare and short-lived, seeding the cosmos slowly with heavier elements needed for more complex structures. But Webb's deep-field images tell a different story. What we're seeing are not just tiny, dim galaxies. They're bright, massive, and surprisingly well organized. This suggests that galaxy formation may have begun far sooner and proceeded far faster than predicted. In other words, the cosmic assembly line was already running full speed within just a few 100 million years of the Big Bang. That could mean the first stars ignited almost immediately after matter cooled, perhaps as early as 100 to 200 million years post-Big Bang, collapsing under gravity far more efficiently than our models suggest. If this theory holds true, it means the universe didn't tiptoe into light. It exploded into it. The first galaxies could have been more numerous, more active, and more luminous than we ever dared to imagine. But that explanation alone doesn't solve everything, because even if galaxies formed earlier, their light still should have been trapped by the surrounding hydrogen fog. So why could Webb see it? That leads to the second possibility. Reionization might have been patchy. In our old models, reionization was treated as a smooth, gradual process, like a fog thinning evenly across the entire sky as dawn breaks. But what if it didn't happen that way at all? What if instead, reionization began in scattered regions, with islands of light clearing the fog long before others? This patchy reionization model paints a picture of a chaotic early universe, a place of contrast and conflict, where some regions were still dark and thick with neutral hydrogen, while others were already transparent, glowing with the radiation of early stars and black holes. In that scenario, galaxies like Jade's GSZ 13-1 might have existed inside bubbles of clarity, local zones where the fog had already been ionized away by intense ultraviolet light. Each bubble could have expanded outward, carving holes in the hydrogen mist, until eventually these glowing patches began to merge, clearing the universe on a cosmic scale. This patchwork version of reionization could explain why Webb sees some regions shining so clearly while others remain shrouded. It means that the universe's first light wasn't a single dawn, but a series of flickering fires spread across space, some blazing early, some still struggling to ignite. The fog didn't lift everywhere at once. It burned away unevenly, like mist under the morning sun. Still, there's a deeper possibility, one that pushes beyond the boundaries of current astrophysics. Maybe we're missing something fundamental in our cosmological models. Perhaps the physics we use to describe the early universe isn't quite complete. After all, the equations of modern cosmology, elegant as they are, rely on assumptions that might break down under the extreme conditions of the cosmic dawn. Maybe gravity behaved differently at that time, especially on small scales. Or perhaps the mysterious components of the universe, dark matter and dark energy, played a role we haven't yet accounted for. Some researchers have even proposed that the early universe may have experienced brief periods of accelerated structure formation, driven by interactions between dark matter and regular matter. If dark matter clumped more efficiently than expected, it could have created dense gravitational wells that pulled gas together rapidly, triggering star formation earlier and faster than conventional physics would allow. Another intriguing hypothesis points toward unknown forms of radiation or energy, exotic phenomena that could have thinned the hydrogen fog more quickly. Perhaps the first black holes emitted jets of radiation powerful enough to carve out channels of ionized space. Or maybe there were early bursts of cosmic activity, events so energetic they changed the thermal and ionization history of the cosmos itself. And then there's the possibility that the problem isn't with the universe. It's with us. Maybe our interpretations, our methods, or even our instruments are revealing a complexity we haven't yet learned to read correctly. Webb's data is so precise, so deep, that it's exposing subtleties we didn't know to look for. Perhaps light being bent, magnified, or distorted by gravitational effects we don't yet fully understand. Each of these explanations carries profound implications. If galaxies formed earlier, then the universe's structure emerged in a cosmic sprint, not a marathon. If reionization was patchy, then the early cosmos was a battlefield of light and darkness, not a uniform glow. And if our models are incomplete, then the universe may still be holding back entire chapters of its origin story, chapters written in a language we're only beginning to learn. But in truth, these theories are not mutually exclusive. It's possible, even likely, that the answer lies in a combination of all three. The first galaxies may indeed have formed early, inside patchy bubbles of ionized hydrogen, driven by processes that our current physics only partially explains. That's the beauty and terror of discovery at this scale. Webb has not given us a single, simple answer. Instead, it has handed us a puzzle written across billions of light years, one that challenges our intellect and ignites our imagination. Every data point is a clue, every galaxy a message from a time when light itself was young. In the end, these possible explanations are just the beginning of the conversation. Because if Webb has taught us anything so far, it's that the universe is far more creative, far more chaotic, and far more intelligent in its design than our equations can capture. It doesn't just follow the rules, it rewrites them. And somewhere out there, in the faint red glow of the ancient cosmos, the answers are waiting, encoded in photons older than time itself. When astronomers talk about the strange clarity of galaxies, like Jade's GSZ 13.1, one of the most compelling ideas they return to is that of cosmic neighborhood effects, the idea that what happens in one small corner of the early universe can differ dramatically from what happens elsewhere. The universe wasn't uniform during its first few 100 million years. It was a patchwork of extremes, regions of intense energy and activity separated by vast stretches of calm, cold darkness. And in those active pockets, local conditions may have evolved so rapidly that they ionized their surroundings long before the rest of the cosmos caught up. In other words, the first galaxies didn't just light up the darkness, they began changing it. Imagine the early universe as a fog-covered valley before dawn. Most of the landscape is still invisible, cloaked in thick mist. But in a few places, fires begin to burn. The heat from those fires pushes the fog back, clearing small patches of visibility around them. The rest of the valley remains dark and hidden, but within those bright pockets, you can suddenly see the world take shape. That's what may have happened with galaxies like Jade's GSZ 13.1. They were the first fires in the fog of creation, surrounded by bubbles of clear space carved out by their own brilliance. These clear bubbles weren't empty voids, they were ionized regions, created by powerful radiation from the earliest stars and possibly the first black holes. The ultraviolet light emitted by these newborn stars was so intense that it stripped electrons away from hydrogen atoms in their vicinity, turning opaque gas into transparent plasma. This process didn't happen evenly across the universe. It began locally, around each new source of light, spreading outward like ripples in a pond. The larger and hotter the stars, the more rapidly they ionized the surrounding hydrogen. And in these early galaxies, the stars were unlike anything that exists today. They were monsters, hundreds of times the mass of our Sun, burning millions of times brighter. These population 3 stars, forged from pure hydrogen and helium, lived fast and died violently, releasing floods of radiation that could ionize massive regions of space in relatively short periods of time. A single galaxy filled with such stars could have created a bubble of ionized gas spanning hundreds of thousands of light years, a bubble through which light, including the distinctive Lyman alpha emission, could travel freely. But it wasn't just the stars that mattered. Many scientists now believe that black holes, the remnants of those massive first-generation stars, also played a pivotal role in shaping these early cosmic neighborhoods. When these black holes began feeding on surrounding gas, they emitted powerful jets and bursts of X-rays and ultraviolet radiation. This energy could heat and ionize the nearby hydrogen even more efficiently than starlight, accelerating the clearing of the cosmic fog. In regions where these two forces, blazing stars and voracious black holes, coexisted, reionization would have been supercharged. These areas became the first transparent windows in an otherwise opaque universe. Meanwhile, other regions, lacking such intense activity, remained dark and dense with neutral hydrogen for much longer. This unevenness, this patchiness, explains why Webb can see galaxies shining clearly from such an early epoch. They weren't necessarily living in a universally transparent cosmos. They were living inside their own locally clear bubbles, each one a pocket of visibility surrounded by a sea of fog. Simulations of the early universe now support this view. They show that as galaxies began to form and cluster together, their combined radiation created overlapping bubbles of ionized hydrogen. Over time, these bubbles merged, slowly transforming the foggy, opaque universe into the transparent one we know today. Webb's detection of Lyman alpha light from JADE's GSZ-13, one could mean that this process was already well underway far earlier than expected, that these first bubbles had already begun expanding, connecting, and reshaping the universe's landscape. And while the idea of cosmic neighborhoods sounds poetic, it also underscores a profound truth about how the universe operates. Environment matters. Not every corner of the cosmos evolved at the same pace. Local density, temperature, magnetic fields, and even the distribution of dark matter all influenced how quickly light could break free. In some regions, gravity pulled matter together efficiently, forming stars that blazed early and bright. In others, the gas may have remained too diffuse to ignite for hundreds of millions of years. These early neighborhoods may also explain why galaxies like JADE's GSZ-13-1 appear so bright and mature. They could have been born in special regions, cosmic intersections where matter was more concentrated, radiation more intense, and feedback effects more dramatic. In such places, galaxies could grow faster, form stars more efficiently, and clear their surroundings long before the rest of the universe caught up. This paints a picture of a universe that wasn't a smooth, predictable gradient of light emerging from darkness, but a chaotic mosaic of brilliance and obscurity, some regions blazing with light, others still veiled in shadow. The cosmic fog didn't lift all at once. It receded in waves, pushed back by the first great lights that refused to be hidden. And here lies the poetic irony. Webb, designed to peer into the deep, dark unknown, has found that the early universe wasn't uniform darkness at all. It was already alive with local brilliance, punctuated by regions of clarity where the first galaxies had already begun rewriting the rules of visibility. So when we look at JADE's GSZ-13-1 through Webb's eyes, we're not just seeing one galaxy. We're seeing a bubble of defiance, a small piece of the universe that became transparent before it was supposed to, a cosmic neighborhood that dared to shine while the rest of existence was still asleep. And it makes us wonder, how many other such neighborhoods are out there waiting to be found? How many other bubbles of early light have already escaped the darkness, whispering across 13 billion years to tell us that the universe's dawn was not a single sunrise, but a constellation of fires igniting one by one across the cosmic night? The discovery of galaxies like JADE's GSEZ-13-1 and the revelation that the universe was already partially transparent so soon after the Big Bang doesn't just challenge a few astrophysical details, it threatens to rewrite the entire timeline of the universe's first billion years. For decades, cosmologists have relied on a well-defined framework that describes the universe's evolution step by step. The Big Bang, the cooling of matter, the formation of the first atoms, the cosmic dark ages, and finally, the dawn of light during the epoch of reionization. Webb's findings, however, suggest that these steps might not have occurred in the neat sequence we imagined, or at least not at the pace we thought they did. If galaxies were already forming and emitting Lyman alpha light just 330 million years after the Big Bang, then the events that preceded them, the condensation of gas, the ignition of the first stars, and the onset of cosmic reionization must have happened much earlier. In essence, Webb has compressed the cosmic timeline, forcing scientists to re-examine the assumptions that underlie our entire story of creation. Let's put this into perspective. According to the traditional model, the Big Bang occurred about 13.8 billion years ago. Roughly 380,000 years later, the universe cooled enough for protons and electrons to combine into neutral hydrogen atoms, a moment known as recombination, when the cosmic microwave background radiation was released. After that, the universe entered the cosmic dark ages, a long, lightless period lasting perhaps 200 to 400 million years. During this time, gravity slowly began to pull matter together into clumps, but no stars or galaxies had yet formed to illuminate space. Then, somewhere between 400 million and 1 billion years after the Big Bang, the first stars ignited. These stars began the process of reionization, slowly transforming the universe from opaque to transparent by ionizing the neutral hydrogen gas. That was the classic picture: slow, steady, predictable. But Webb's data has torn a hole in that narrative. By observing galaxies like Jade's GSZ 13.1 at redshift 13, Webb is effectively seeing the universe when it was less than 3% of its current age. Yet in that infancy, we already find not just starlight, but clear evidence of ionized hydrogen, meaning that reionization was already underway, perhaps hundreds of millions of years earlier than anyone expected. This discovery suggests that either 1. The first stars and galaxies formed astonishingly quickly, or 2. The process of reionization was uneven, with some regions lighting up much sooner than others. The implications of this are staggering. If reionization began earlier, then our models of structure formation, how gas collapses under gravity to form stars and galaxies, may be fundamentally incomplete. For galaxies to form this quickly, the density fluctuations in the early universe must have been stronger than predicted, allowing matter to gather and ignite stars faster. That, in turn, could mean that the seeds of cosmic structure, the tiny ripples in density that grew into galaxies, were laid down differently than the current lambda cold dark matter model suggests. Alternatively, if reionization was patchy, then the early universe was a far more dynamic and complex place than we've given it credit for. Some regions may have reionized early, powered by clusters of bright galaxies or active black holes, while others lagged behind, remaining dark and neutral for hundreds of millions of years. In this uneven dawn scenario, the universe didn't transition from opaque to transparent all at once. It flickered, like stars emerging one by one through dissipating clouds. This would fundamentally change how we interpret the cosmic background radiation and other large-scale signals that describe the early universe. For example, if reionization was uneven, it would have left subtle fingerprints on the cosmic microwave background, CMB, small distortions that could help astronomers map which regions of space cleared first. Future missions may be able to detect those imprints, giving us a kind of weather map of how the fog of hydrogen lifted over time. But there's an even deeper implication. If the universe became transparent sooner, then it also became structurally mature sooner. That means galaxies, stars, and possibly even black holes were forming and evolving at breakneck speed in the first few 100 million years. The cosmic timeline we've used for decades, with its neat division between the dark ages, the first light, and the growth of galaxies, might actually be more of a cosmic overlap, with multiple processes happening simultaneously. It's as if the universe's first billion years weren't a calm unfolding of events, but a cosmic storm, chaotic, turbulent, and filled with rapid transformation. Light and matter weren't politely taking turns. They were battling for dominance in a universe struggling to define itself. Stars ignited, black holes roared, and radiation carved holes through the fog, all while the first galaxies were still forming. This realization also opens profound questions about dark matter and dark energy, the mysterious ingredients that make up 95% of the universe. Our models depend on how these forces shaped the early cosmos, how dark matter's gravity seeded structure, and how dark energy influenced expansion. If reionization began earlier or proceeded differently, it might hint that our understanding of these forces is incomplete. Perhaps dark matter interacted more strongly with normal matter in those early epochs, or perhaps dark energy's effects varied over time. The bottom line is this: Webb's discoveries are forcing cosmologists to rebuild the timeline of the universe from the ground up. The neat sequence of events that once seemed so certain — darkness, first light, reionization, structure formation — is dissolving into a far more complex and accelerated story. It's possible that cosmic reionization began not at redshift 10 or 9, but as early as redshift 15 or higher, when the universe was barely 200 million years old. That doesn't just shift our understanding of when the universe became visible, it redefines what we mean by the beginning itself. If galaxies were already forming that early, it suggests the universe wasted no time organizing itself into structure, complexity, and light. It was primed for creation from the very start. And this, perhaps, is the most profound implication of all. The Big Bang wasn't just the birth of matter and energy. It was the birth of possibility. The cosmos didn't stumble into light slowly and cautiously. It erupted into it, driven by forces we are only beginning to understand. So now, as Webb continues to scan the distant reaches of space, every faint red smudge it finds could be another clue, another piece of evidence that the universe's first billion years weren't what we thought. The cosmic story is being rewritten before our eyes, and its new version is richer, faster, and far more dramatic than anyone dared to imagine. As breathtaking as Webb's early discoveries have been, they are only the beginning. The James Webb Space Telescope's first year of science has already rewritten cosmic history books. But what lies ahead promises to push the boundaries of knowledge even further. Astronomers are now gearing up for the next phase of JWST's grand mission, to test these discoveries, confirm what's real, and search for more ancient galaxies showing the same mysterious, impossible signals of light, especially those unexpected Lyman alpha emissions that challenge everything we thought we knew about the early universe. In scientific terms, Webb has done something extraordinary. It has opened an entirely new era of observational cosmology. But with every new discovery comes a flood of new questions. Was JADE's GSZ 13.1 unique, or are there many more galaxies like it scattered across the deep universe? Was the Lyman alpha light we detected a rare local anomaly, or is it a clue to a much broader, faster process of early reionization? And perhaps most crucially, if galaxies like this were already shining through the fog 330 million years after the Big Bang, how early did the first galaxies really form? To find out, Webb's upcoming observation cycles, particularly through large-scale programs like JADE's DEEP, SEERS, Cosmic Evolution Early Release, Science, and NGDEEP, Next Generation Deep Extragalactic Exploratory Public Survey, are set to probe even deeper and wider fields of view than before. These surveys will scan the skies for galaxies at redshifts even greater than 13, potentially reaching redshift 15, 16, or beyond, corresponding to just 250 million years after the Big Bang. Each of these new targets will be carefully analyzed using Webb's most sensitive instruments, NIRCam, Near Infrared Camera, will identify faint, distant galaxies based on their color signatures. Those distinctive dropouts, where shorter wavelengths vanish because their light has been stretched beyond the visible spectrum. NIRS-PEEC, near-infrared spectrograph, will then take over, splitting that ancient light into its component wavelengths. This allows astronomers to measure precise redshifts, confirm distances, and detect key spectral lines such as Lyman alpha, hydrogen beta, and oxygen 3. Clues that reveal whether these galaxies are forming stars and how much of their light can escape into the surrounding cosmos. What scientists are most eager to find are patterns. If more galaxies show the same kind of strong, early Lyman alpha emission that JADE's GSZ 13-1 does, it would confirm that the early universe wasn't uniformly opaque after all. It would mean that reionization truly was patchy and uneven, with multiple bubbles of light expanding at different rates across the cosmos. On the other hand, if Lyman alpha emissions turn out to be rare, appearing only in isolated regions, then JADE's GSZ's 13-1 may represent an exceptional environment, perhaps influenced by powerful local radiation sources, such as early quasars or black holes. Another key goal is to measure how widespread these clear bubbles were. Were they small, individual regions carved out by single galaxies, or large-scale networks of overlapping ionized zones created by clusters of galaxies working together? To answer this, JWST will need to build a kind of map of reionization, tracking how transparency varied across space and time. Projects like the Cosmos Webb survey, which covers an area hundreds of times larger than the JADES field, will help fill in that picture. While JADES focuses on deep, narrow fields to capture faint, ancient galaxies, Cosmos Webb will trade depth for breadth, mapping tens of thousands of galaxies to understand how widespread these early structures really were. Together, these complementary views will help scientists trace the architecture of the early universe. When and where the first pockets of light formed, how they merged, and how quickly they transformed the cosmic fog into transparency. There's also a growing focus on spectral fingerprints beyond Lyman alpha. JWST's data can reveal other emission lines that hint at the chemical makeup of these galaxies. For instance, the presence of oxygen, nitrogen, or carbon tells scientists that earlier generations of stars have already lived and died, enriching their surroundings with heavier elements. Detecting such metal lines in extremely early galaxies would mean that multiple waves of star formation had already occurred far sooner than our models predict. And then, of course, there's the quest for the first stars themselves, the legendary population 3 stars that no telescope has ever directly observed. These stars are believed to have been massive, hot, and short-lived, producing enormous amounts of ultraviolet radiation that helped trigger reionization. If Webb can find indirect evidence of them, through their spectral imprints or the chemical traces they left behind, it would represent one of the greatest breakthroughs in astrophysics, the first direct glimpse into the universe's original generation of starlight. Webb's search will also extend to early black holes, those mysterious engines of radiation that may have formed surprisingly soon after the Big Bang. Some astronomers suspect that these black holes, rather than stars alone, could have played a major role in ionizing their neighborhoods. Webb's sensitive infrared detectors can look for the telltale signs of active galactic nuclei, AGN, in early galaxies. Bright emissions powered by matter spiraling into massive black holes at their centers. Finding such AGN in extremely early epochs would revolutionize our understanding of how black holes formed and grew alongside galaxies. But beyond individual discoveries, what's truly exciting is what this next phase of Webb's mission represents. Each new detection isn't just another point of light. It's another data point in a grand reconstruction of cosmic history. With every observation, JWST is giving us a clearer, more intricate picture of how light spread through the universe, how the fog lifted, how galaxies ignited, and how order emerged from chaos. Already, teams are preparing coordinated campaigns to combine Webb's deep field data with observations from other telescopes. Instruments like ALMA, the Atacama Large Millimeter/Submillimeter Array, and the Nancy Grace Roman Space Telescope will complement Webb's infrared insights by studying the cold gas, dust, and large-scale structures surrounding these ancient galaxies. Together, they'll form a multi-wavelength, multi-dimensional map of the early universe, one capable of testing whether the strange transparency Webb observed was a local phenomenon or a universal phase transition. And if Webb continues to find evidence that the universe was lighting up faster than we thought, if more galaxies show clear Lyman alpha signals at impossibly early epochs, then the next challenge will be even more profound, rewriting the physics that explain how it all happened. Because ultimately, every photon Webb captures is a messenger from the past, a whisper from a time when the universe was just learning to shine. And as those whispers grow louder, as more galaxies come into focus, the story they tell will either confirm or completely reshape our understanding of cosmic dawn. The James Webb Space Telescope was built to answer questions about the first light. But what it's actually doing is far greater. It's forcing us to ask better ones. When the faint glow of Jade's GSZs 13 first appeared in Webb's data, it may have seemed like just another distant smudge among the stars, a tiny flicker in a sea of countless others. But as astronomers began to unravel its light, they realized this wasn't merely a distant galaxy. It was a cosmic revelation, a messenger from an era when the universe itself was still taking its first breath of illumination. And now, with every new analysis, one truth becomes clearer. This single galaxy has the power to reshape our entire understanding of how and when light reclaimed the universe. It's not just about Jade's GSZs 13 as an isolated discovery. It's about what it represents. The unraveling of a cosmic timeline that once seemed fixed, the rewriting of the story we thought we knew by heart. For decades, astronomers believed they had mapped the grand sequence of cosmic dawn, the birth of the first stars, the emergence of galaxies, and the slow clearing of hydrogen fog during the epoch of reionization. The process was supposed to unfold gradually, over hundreds of millions of years, like the sun rising slowly over a misty landscape. But Webb's discovery changes that narrative entirely. What we see now suggests that the universe lit up far more rapidly and dramatically than our models ever predicted. It's as if the cosmic dawn wasn't a gentle sunrise. It was a sudden ignition, a wave of fire sweeping across the darkness, transforming the very fabric of existence. This one galaxy, tiny, ancient, fragile, may be the spark that exposes how incomplete our cosmic history truly is. Because if Jade's GSZ 13-1 was already shining through the fog only 330 million years after the Big Bang, then the forces that cleared that fog, that made the universe transparent and visible, must have begun acting much earlier. The first stars might have formed within 100 million years of creation itself. Reionization might not have been a slow universal process, but a patchwork of fierce local awakenings, where light fought its way through the fog in fits and bursts. That realization forces us to reimagine the character of the early universe. It was not a uniform expanse governed by steady, predictable laws. It was a turbulent frontier, a cosmic storm of formation and destruction, where matter clumped, ignited, and tore itself apart in a race toward illumination. Galaxies weren't just passive observers of that transformation. They were the architects of it. Every star that was born, every supernova that exploded, every black hole that fed on gas, all of it contributed to clearing the fog, one photon at a time. Jade's GSZs. 13-1 is, in essence, a snapshot of the universe awakening to itself. It represents a moment when darkness began to lose its grip, when the first light managed to travel freely through space and proclaim, "I exist." That's why this discovery feels so profound. We're not just observing a distant galaxy, we're witnessing the very act of the universe becoming visible. The broader implications are staggering. Webb's findings suggest that cosmic reionization, the great event that made the universe transparent, might have started hundreds of millions of years earlier than we thought. That means the first galaxies didn't just appear earlier. They may have been larger, brighter, and more influential than we ever imagined. These early systems could have shaped the evolution of everything that followed, seeding the large-scale structures of the cosmos and determining how matter and light interacted for billions of years. Even more astonishing is how this forces us to reconsider our place in that story. The light from Jade's GSZ 13-1 began its journey more than 13.4 billion years ago, long before the Milky Way existed, long before Earth, long before the atoms in our bodies had even formed. And yet, that same light is now reaching our telescopes, carrying the record of a moment when the universe was young and bold and utterly new. Every photon Webb captures is a cosmic time capsule containing the memory of creation itself. But beyond the data, beyond the graphs and redshifts, there's a deeper truth. Discoveries like this remind us that the universe is not finished revealing itself. For all our equations and models, there is still mystery woven into every corner of the cosmos. The fact that one small galaxy can overturn decades of scientific consensus is both humbling and exhilarating. It tells us that the story of the universe is still being written, and we're reading it for the first time, one discovery at a time. And it's not just about science. There's a poetic beauty in realizing that light, born in the chaos of the first stars, has been traveling for billions of years through expanding space just to reach us now, to tell us how it all began. Webb is not simply observing. It's listening to the echoes of the universe's first words. Through that listening, we're beginning to hear a story older and grander than we ever dreamed. A story in which creation itself seems to happen faster, fiercer, and more passionately than we imagined possible. Jade's GSZ 13-1 may be just one galaxy, but it's become a symbol of something far larger. It represents a turning point in how humanity sees the cosmos, not as a static relic of ancient times, but as a living, breathing history that continues to surprise us. It reminds us that the universe is not a solved equation, but a vast, unfolding narrative, and that even after centuries of exploration, we are still only at the beginning of understanding it. Perhaps that's the greatest gift of all. Because in discovering that the early universe lit up sooner than we thought, we've discovered something equally profound about ourselves. That our curiosity, our imagination, and our need to seek light in the darkness are as ancient as the cosmos itself. The story of Jade's GSZ 13-1 isn't just the story of one galaxy. It's the story of light reclaiming the universe, of visibility itself being born. And every time Webb peers deeper into that ancient glow, we're reminded that the universe's first light never truly faded. It's still out there, traveling across eternity, waiting for us to find it, to understand it, and to wonder. When we look at the images captured by the James Webb Space Telescope, what we're really looking at is time itself, the long memory of the universe made visible. Each faint point of light, each hazy arc, each delicate swirl of ancient galaxies represents not only a location in space, but a moment in history. And yet, beyond the beauty of these images lies something even more profound. Webb is not just showing us the past, it's changing our understanding of it. For centuries, humanity has looked up at the stars, and tried to trace the story of where we came from. We have built instruments of ever-increasing precision, each one a little better at capturing the whispers of ancient light. Hubble gave us our first breathtaking glimpses of the deep universe, but Webb has gone beyond what anyone thought possible. It has turned the night sky into a time machine, one capable of piercing through 13.4 billion years of expansion, through fog and distance and darkness, to reveal the first glimmers of creation itself. And what it's showing us is both humbling and exhilarating. The universe is not a quiet place that unfolded slowly according to our neat equations. It's alive, dynamic, chaotic, unpredictable, and far more creative than our theories could ever capture. The discovery of J, A, D, E, S, G 13.1 and its luminous, impossible light has made that clearer than ever. The cosmos did not wait patiently for the right conditions to form galaxies. It did not unfold according to the slow, methodical rhythm we imagined. It raced toward illumination, bursting into light as soon as it could, and maybe even before it should have. That is what Webb is revealing. A universe that is bolder, faster, and far more astonishing than we ever dared to believe. The fog that once seemed impenetrable is thinning before our eyes, and behind it, we're discovering not the cold machinery of physics, but a story full of drama, energy, and mystery. A story that speaks of creation as an act of urgency. Every photon that Webb captures has been traveling since before there were planets, before there were elements heavier than hydrogen and helium, before even time and distance meant what they do to us now. These photons were born in the fires of the first stars, cosmic pioneers that ignited in a universe still dense and dark. They traveled across 13 billion years of cosmic history, through the expansion of space itself, until finally they struck Webb's golden mirrors. In that instant, the story they carried was no longer just the universe's. It became ours too. To look at these photons is to look into a mirror made of eternity. When we see those ancient galaxies, we're not just looking at the past, we're touching it. We're witnessing the first light that ever existed, the same light that allowed everything else, stars, planets, life, and us, to come into being. That light has been on its way since before there was an Earth to receive it. Now, through Webb, we've finally opened our eyes wide enough to see it. But what makes this so awe-inspiring is not just the distance or the age of that light. It's the mystery that it carries, the way it contradicts, surprises, and redefines. Each new discovery Webb makes feels like a revelation and a riddle at the same time. We expected a universe that unfolded like a story we could summarize. Instead, Webb has given us one that resists simplicity, a universe that refuses to be understood too easily. Galaxies forming earlier than expected, stars shining through hydrogen fog that should have been impenetrable, regions of space that became transparent long before the rest of the cosmos. These are not just anomalies, they are signposts pointing toward a deeper, richer truth. They remind us that science, at its core, is not about confirming what we already believe. It's about confronting what we never imagined could be true. And that is what Webb does best. It doesn't merely collect data, it invites wonder. It reminds us that there is still so much we don't know, and that ignorance, far from being a limitation, is the engine of discovery. The telescope has turned our ignorance into light, transforming the unknown into something tangible, beautiful, and profoundly humbling. The awe comes not only from what Webb reveals, but from what it implies. When we see the first galaxies lighting up the darkness, we're not just witnessing an astrophysical process, we're seeing the origin of visibility itself. We're seeing the moment the universe began to speak in light. It's as if the cosmos, silent for hundreds of millions of years after the Big Bang, finally found its voice. And that voice has been echoing ever since, growing louder, more complex, more magnificent, until it became the vast cosmic symphony we live in today. And here we are, tiny beings on a small blue planet, finally able to hear the first notes of that song. It's almost poetic that Webb, itself a fragile construct of metal, silicon, and glass, drifts silently through the vacuum of space. A creation of our hands that now gazes upon the creation of everything. From its vantage point, 1,000,000 miles from Earth, it looks out across time and captures light that began its journey before even the atoms in Webb's own mirrors existed. There is something deeply moving in that. The thought that human curiosity has reached so far that we've built a machine capable of seeing the birth of light itself. It's hard not to feel awe in the face of that. Awe not only at the universe's scale, but at its continuity. The same physical laws that govern the stars govern us. The same atoms that once burned in the cores of the first galaxies now reside in our bones. The same photons that raced across billions of years now pass through the detectors of a human-made telescope, and in doing so, connect our present to the universe's first dawn. Webb has made us witnesses to that connection. It has shown us that time is not a barrier, but a bridge. That even after billions of years, light remembers its origin. It carries history in its wavelength, memory in its energy. And by decoding that light, we are not just studying the universe, we are participating in it. That realization redefines what it means to explore. For centuries, exploration meant crossing oceans, climbing mountains, or sending probes to new worlds. But Webb has expanded that horizon beyond anything physical. Its discoveries remind us that to explore is also to look backward in time, to chase the light of beginnings. It shows us that the universe is not distant, it's deep. And depth, unlike distance, is something we can always travel further into. Every time Webb gazes deeper, it's not just adding another page to the story of the cosmos. It's rewriting the opening chapters. It's forcing us to rethink what we thought was fixed. When galaxies formed, how light escaped, when the fog lifted, and even what beginning truly means. Each discovery pulls the veil a little further back, revealing that creation is not a single moment, but an ongoing act, one that continues to unfold before us, through us, and within us. This is why Webb's mission transcends science. It touches something fundamental in the human spirit, that ancient hunger to know, to see, to understand our place in the infinite. Every image it sends back is more than data. It's a revelation that we are, in some small way, a part of the universe's self-awareness. Through our eyes, through our instruments, the universe is looking back at itself, seeing its own reflection in the mirror of time. And so, as the James Webb Space Telescope continues to stare into the abyss of the past, what it's truly revealing is the miracle of continuity, that the light of the first stars still travels, still speaks, still transforms. It is showing us that even in the vastness of space, nothing is ever truly lost. The light that left those first galaxies billions of years ago has found us, and in that encounter, the universe becomes conscious of its own history. So when we say that Webb has looked too deep, what we really mean is that it has looked deep enough to show us ourselves, not in a literal sense, but in the realization that everything we are was once part of that first light. We are not separate from the cosmos. We are its continuation. And that is the true meaning of awe. Because every time Webb looks deeper, it doesn't just see the past. It changes our future understanding of it. Each new discovery redraws the boundaries of what's possible, illuminating both the universe's history and the reach of human curiosity. The fog is lifting, and what's emerging is beyond anything we imagined. As that light continues to arrive, Crossing time and space to touch us here, one truth remains. The universe has always been luminous. We just needed to build something powerful enough and brave enough to finally see it. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.